Okay, so welcome to the last day of this crazy tutorial series. Finally, we're on day three. Today will be the last day, and if I were you, I'm not going to miss any of the lectures for today. So before we start with today's business, is there any questions from previous sessions, any of the previous session, or probably when you were looking at stuff, you came across something that you need clarification, or probably I said something that is not sitting well with you. Please, in the next 1 or 2 minutes, let us use that to answer some questions. All right. So if you have any question, please bring it up. Okay. Yeah, if you have any questions, please let's hear you. All right, Elijah. Oh, okay, Elijah just joined. Yes, any questions, please? Any questions? Any questions? Any questions? Yes, please. If you have any questions, you could go ahead and ask, or maybe you have some. You learned something new on your own. You want to share with the rest of the team. Yeah, Patil. I don't know if I have asked it. I've mentioned it right. Please go ahead. Yes, please. You can ask your question. I thought somebody wanted to ask a question. Oh, please, just go ahead, okay? If you want to ask a question, just go ahead. If you could get access to a notebook, please get one, okay? So that you can jot some stuff that we're going to discuss today and jot them down because they will help you a lot in your PCB design journey. Okay, so if you could get a pen and a book, please get it. Okay. I thought this thing was going to switch. If you could get a pen and a book, please get it so that. Uh, hmm. All right. If there is no question, then let me just quickly get into action. Where's my mouse? Okay. So, who remembers where we ended yesterday? Yeah, if you remember where we ended yesterday, please tell us something. If you started today too quiet, my PC is just misbehaving a little. That's why I'm trying to resolve. So let's keep it coming. If talk to me. Yesterday, what did you learn? Where do you remember? Where did we left? Living tired. Yeah, please talk to me. Talk to me.
Okay.
Yeah.
Good morning. Good morning, everyone.
Yeah. Good morning.
Yeah. So yesterday we were trying to build an Arduino Uno board. So yesterday we concentrated on the schematic, though the placement of the PCB component, how to do the footprint, and to annotate those footprints, and also how to draw the board edge for the PCB and the placement of the PCB. So that is what we achieved yesterday, and today we are to route the PCB.
Thank you very much. Thank you very much. Thank you very much. Okay. So yeah, actually everything is said is true. Everything is said is true. This is really going to disturb me like this today. Everything is said is true, and I'm hoping we could do finish with our but definitely we have to finish work area, please connect to this. Thank you. All right, that's fantastic.
Hello, sir.
Yes, sir. Yes, sir.
Yeah, I have a question.
Okay. Good.
I missed some sessions, so why going I ESP32 stuff like that? Not on.
Yes.
Okay. I want to ask that is there any firmware after building the ESP board? Is there any firmware we need to upload and read for
So
the ESP before it can function?
I think the ESP has this. You can you there. I don't know exactly how they call it, but there is something on it. For an Arduino, I think you have to load the bootloader. With the ESP, I think you have to flash it with a program. Okay, but I haven't done much into that. I just use it. Okay, so they have some program they flash it with before it can begin to accept commands and also respond to your codes. At least I know that, but that side of things I haven't actually done much. I don't know if that is okay with you. I haven't done much on that
Okay.
side.
Yeah.
Yeah.
Yeah. Why I'm asking this is, all these the ESP board. I mean, if I don't want to use, maybe I want to do a real project and I don't want to, that board is too cumbersome. I mean, it's too big for my likeness.
Yeah.
Maybe I want to design my own board and I need to implement something like ESP32, but I
Mm-hmm.
want to do it in my own form to
Oh,
make my
oh,
it
okay, okay, okay. I actually get you
yeah.
now. So actually, if you use the IC, not the dev board, the IC actually comes pre-programmed. So once you have a pre-programmed IC, you can just go ahead and load your code onto it. Okay, you don't have to do anything. Yes. Uh,
Okay.
I actually don't also use the dev board anyways. I use the ICs direct.
Okay.
The SOCs, I use them
Okay.
directly. Just one more setting. I don't want that thing popping up every time. Okay. I need a supercomputer, seriously. I just need a supercomputer. Yeah, any other
Prof.
questions? Yes, sir. Yes, sir.
Yeah, so meaning the Atmega 328 and the ESP32, you don't have to be uploading any firmware on your own. After embedding it in your project, you can just go ahead and upload your code
So,
without worrying yourself about any firmware this thing.
yeah, Arduino, if you want to, the Atmega 328, if you want to use program it via USB, you have to load something called a bootloader. Okay. But then, if you want to be programming with the ISP or ICSP header, then you actually don't need a bootloader. Actually, for this microcontroller, the program you are creating is actually its firmware. Okay, just that for the case of ESP32, yeah, they have something like, if I may call it, a BIOS, okay, for it, that makes it work well. So sometimes if you're going to use it for MicroPython, you have to flash the MicroPython whatever on it if you want to use it for C++. But by default, it comes with the C++ or the IDF program installed or something. So you just go ahead and write your code onto it. Okay, so usually those are not things you have to worry so much about. Okay, but like I said, that side of things I don't usually go there. So yeah. Okay, so thank you
Okay.
very much. Thank you very much. Stop presenting. I think we can start now. All my systems are ready now. Okay. So today we're going to start our PCB routing, okay? But there are a couple of stuff that I want you to understand, and these are fundamental principles of electronics. Wow. From this shaking. Do you see my screen blinking?
Yes, please.
Is it still doing that?
Yeah,
Stable
it just
now.
stopped.
Okay. Wow. A lot is happening magically. Okay. So let me quickly launch our key card and show you where we've gotten to so far and what is the plan for today. Okay, so as our friend rightly said yesterday, we only what where we ended, we arranged the components on the board, we designed the board outline. So right now, and the components actually have been optimized and ready for routing. Okay, but I know some people already understand these things, and then yeah, they will probably need us to go straight to the thing. But for the sake of those who are very curious and the beginners, I'm going to talk about something real quick, okay? And not it may not be very real quick, probably to take the first session, but it's the most important information you need when you are routing PCB. I mean, routing the PCB is just a matter of connecting these lines, right? But we don't actually just connect these lines. There is a fundamental physics behind it that you need to understand so that you can route perfectly, if I may put it. Okay. So before we come to the business of the day, let us go and check out those concepts. Please, there are a lot of mathematical stuff around it, but I'm going to stay away from the mathematical stuff. If you are interested in all the mathematical details, Zach Peterson has a lot of interesting videos with Altium. I think if you go to Altium Academy, they have very interesting video tutorials. And actually, we have our theory platform where we do all these PCB design theories and techniques. That's PCB Africa. If you are not yet a member, please join that page too. We have the likes of Daniel Baker, Zach Peterson, and the likes doing presentations over there. Okay, there are very beautiful tutorials over there. Please check it out on YouTube, subscribe, and then follow us. Okay, so Let's Route is going to be like the practical sessions of PCB Africa. Is that okay? So joining the two platforms will be the best for you. So if you want details on the mathematics and why things work the way they are, please follow Zach Peterson on Altium Academy. Check out PCB Africa tutorials. Daniel Baker has great tutorials on those things. Okay, but right now I'm just going to give you the concept, fundamental concept. Where there is a need for a little bit of mathematics, I'll just keep it on the down low just to explain the ideas. Is that okay? And I need this session to be very interactive so that I can know whether you are getting the thing or not. Is that okay? I don't want this to be one of the sessions where I speak and you listen to me. Okay, I need you to uh, follow through. Okay, all right. So let's get started. So who has heard of maximum power transfer theory? Who has heard of it before? And what is it about? Maximum power transfer theory. If you've heard of it before, Please, what did you hear about it and what is it about? Yeah, maximum power transfer theory. Mm-hmm. Talk to me. There are the video is being recorded. Is that okay? So when I ask for your input and there is so much delay, it will make watching the recorded video boring. Is that okay? So please, if I ask this kind of stuff, let's be snappy about our responses. Okay. All right. So yes, maximum power transfer. Who has heard of it? Hmm. Maximum power transfer. Yes, if you've heard of it before, please. Yeah. Yeah, Christine, let me hear from you. Christine, go ahead.
It is to generate the maximum external power through a resistor, an internal resistor.
Mm-hmm. Okay. Okay. I think you have an idea. We'll put some polishing on it. Okay. Thank you very much. Thank you very much. Yeah. Any other maximum power transfer theorem? If you've heard about it or know what it means, please let me hear from you. Okay.
Can you hear me?
Yeah, Nat, go ahead.
Okay, it states that to obtain the maximum external power from a power source
Okay.
with an internal resistance,
Okay.
the resistance of the load must be equal to the resistance of the source.
Fantastic. Thank you very much. Okay. Now, what I'm going to do for this session, it's going to be in the form of a cascade. Okay. One depends on the other and that in that order. So please make sure you don't miss. Okay. If you miss the foundation, just draw my attention to it. Is that okay? All right. So whenever, let's say I have a system, I have a battery. Okay. I have a battery and then this battery is connected to some form of load. Here let's use a light bulb. Is that okay? Let's use a light bulb for this. Okay, now this battery will provide a voltage V and a current of I is going to be transmitted. Remember on the first day I said that the main job of an electronics designer, a circuit designer, is to move energy. Okay, we are moving energy from this source, please forgive my writing, to this load. So this is our load, this is our load, this is our source. Okay, now unfortunately, if we move about 100, let's say if we move 100% of power from here, we will end up with about 90% getting to the load. Is that okay? The reason is that we have some discrepancies in our network or in our transmission that leads to dissipation or loss of part of the power that we are trying to transfer. Is that okay? Now, unfortunately, uh, in real applications, this is not something that you can prevent. Is that okay? The reason is that sources, number one, sources, which is our batteries and stuff, are not perfect. Is that okay? Sources are not perfect. And by they not being perfect, what I mean is that any energy source that you could use physically will have some internal impedance. Okay, for now, I'm going to talk about internal impedance. Okay, now impedance here is the general term given to any form of resistance. Is that okay? Now, when we talk about impedance, three things usually come to mind. So the usual ones that probably most of you know would be resistance. The usual one would be resistance, which yesterday we learned that there are components called resistors that we can get from them. And also we also learned that every material has some form of resistance. Is that okay? The copper lines, the copper wires, all these things have some inherent resistance. And for resistance, usually it is also a factor of the length that and the size that you choose. Is that okay? Another form of resistance, we call it reactance. Now, there are two forms. We have what we call the capacitive reactance, which is like, if I may crudely or vaguely put it, take it as resistance due to capacitors. Okay, due to capacitors, or resistance from capacitive devices. So this is due to capacitors. So here, capacitive reactance. Okay, and reactance. Sorry, and the other one is what we call inductive reactance. Okay, so whenever we talk of impedance, it's a general term for these things. However, I know most of you know of only resistance. Now, the reason that is so is because in most of the things that you have probably worked on, you are working with DC applications. So your frequency is almost zero. Okay, your frequency is almost zero. Now, the moment there is no frequency in the picture, then these guys can be eliminated and you only have this at play. But if the frequency of your circuit or that you are dealing with is not zero, then you will not just have resistance to deal with. You also have what we call capacitive reactance and inductive reactance, which are all forms of impedance. Okay, now we will come to that. So every energy source or the sources, they have their internal resistance. Okay, and in this case, we only consider, since we are dealing with a DC source, that means we are talking of only resistance. We are not even going to consider the capacitive and the inductive resistances. Okay, so there is a concept in electronics called Thevenin equivalent. Okay, what it simply means is that if I take any source, I can model it as some battery and some battery with a resistor in series. Okay, so let's call this resistor Ri. So that's the internal resistance of the battery. Okay, so per Thevenin's module, this whole thing now represents our source. Okay, a battery with a resistor in series. So we'll call this VTH, voltage Thevenin, and actually let's change this to RTH. Is that okay? So when we connect this to a load like that, let's say a bulb, then we have to actually worry about how much power can be delivered to this load. Is that okay? Now, let's assume that their voltages actually match. Okay, so this load is a resistive load which has an internal resistance of RL, and when we connect this, a current of I is going to flow. Is that okay? You see, if you consider this circuit, if we try to find what voltage, the voltage that would appear here, let's ground this point. The voltage that is going to appear here is going to be the voltage that is going to power up our bulb. Is that okay? So the power that we are transferring, under what condition can we have maximum power? We know that definitely we cannot transmit 100%, right? But what is the maximum that we can transfer? Is that okay? So in other sense, what configuration of this circuit can make it possible to transfer maximum power through this system? Now I'm talking about this because when we start with the PCB, you're going to hear of impedance matching. Okay, and the concept of impedance matching has to do with maximum power transfer theory. Okay, that's why I'm explaining this. So let's check out some scenarios. Okay, so let's say, but before that, we know power to be equal to current times what? Voltage, voltage like that. We can also express it in terms of I squared times R, the square of the resistance times R. And I think we can also express it as V squared over R. Yes. You can also express power. So these are the various ways we could express power. Is that okay? So case one, assuming we choose RL so that RL equals to 0 ohms, what do you think would happen? Under what situation can you think of where RL will be 0 ohms? Yes. If you have any idea, just go ahead. Under what situation can you think of such that RL here would be 0 ohms? So we are looking at situations where we can get maximum power, okay? So the first scenario that we are looking at is when the load, the resistance of this load is 0, okay? Yeah, so under what situation can you think of this? Okay, so if this resistance is 0, then from here, okay, we can know that, okay, no matter what amount of current flows through, if we multiply that amount by 0, our power is going to be what? 0. Is that okay? So it means that if we choose if the component that the load, okay, so this thing here that we have represented by RL represents a load, a resistive load, something like a light bulb. Is that okay? So what this means is that if we choose a device, if we place a device here and that device has 0 resistance, then in the end we are going to have 0 watts of power transferring through it. So that means nothing is going to happen. And actually it makes sense. The only reason it makes sense, okay, how does it make sense? If the resistance is 0, then from Ohm's law, the voltage that will drop across this is given by V times what? IR, right? And we know I, so there will be I, but R is going to be 0. That means the voltage drop across it is going to be 0 volts. Is that okay? So my question is, under what circumstance would this V out be equal to 0? Under what circumstance would this V out give us 0? Yes, any ideas here? If you really understand circuits, right? Under what circumstance can we have a 0 volt at this point when we even have something here, a load here? Yeah, Nika, go ahead.
If our circuit short circuit.
Exactly, fantastic. Okay, so if we have 0 volts here, then that means that it's almost like we've connected a wire from here to ground, bypassing this device. Now, if we have such a scenario, it means that all the current is going to flow through here because naturally current will always take the path of minimum resistance. Okay, it's a law of nature. Current will always follow the path where it faces minimum resistance. And even you human being, if you get a chance of not doing anything, you will probably choose that over the chance of doing something that takes your time and your energy. Okay, it's something natural. Okay, so but the only reason, the only situation where we can have 0 here is that we have short circuited this. And it also makes sense because we said that assuming our load has 0 resistance. If our load has 0 resistance, it just means that we have short circuited it. In that case, as we have seen here, we are going to have 0 power transfer. Is that okay? So there will be no power transferred if our resistance is 0. The resistance of our load is 0. That's case 1. Please, if you have any question, ask, because I'm going to clean this. I'm going to clear this. If you have any question, ask. Any questions? Any questions? Okay, good. Now, the second case that I'm going to, can I create? Okay, yeah, Elijah, go ahead. Go ahead.
Sir, please, I'll be glad if you take that side again. I'm a bit confused.
Okay, okay. All right, please, I'm going to try again. Don't be confused again, okay? All right, so can I create a new sheet? Close this. Enoch, can I create a new sheet, new note?
Yeah, yeah.
Yeah, how are you doing?
I'm okay.
Okay, so The tablet you bought is what I'm using, so clap for yourself.
Okay, that's great. That's good
Anybody
to know.
knows any way I could clear these things? Or probably create a new sheet or something. I just installed this. Okay, let's see, Control N. That's nothing. Okay, let me just probably, oh, can I? Oh, good. I know definitely there's a better way of doing this. That's all I know right now. Yeah, so please, I'm going to take that again. Okay, so try and then pay attention. Okay, follow. Oh, come on. We really, okay, Control A, delete. It always works. All right. So this is what I'm saying. In the circuits, in the PCB, you'll be hearing about terms like impedance matching. Is that okay? So I want to explain those concepts before we even get there so that when we get there, it doesn't look new to you. Now, what I'm saying is this. Whenever we have a power source, so let's say we have a battery, right? This battery is not actually a perfect source. So all the sources that you could think of, no matter what kind of source it is, has some internal impedance. Now, because we are dealing with a DC scenario, we will just restrict ourselves to resistivity. Is that okay? Internal resistance. I just explained what the kinds of impedances that we have. Okay. So we can, according to a certain gentleman who is dead a very long time ago, called Thevenin, we can model. Okay, in engineering, we model a lot. Okay, so in place of the battery, we can model it as a cell, a battery with a resistor in series. So let's call this VTH, which means, so let me define my parameters here. VTH here means Thevenin voltage. Okay, that is the voltage according to the model that we have. Okay, Thevenin voltage. And then we have RTH, which we call Thevenin or Thevenized resistance. Thevenin resistance. Okay, a resistance, yeah. Okay. So now, if we hook this to a load, let's say a resistive light bulb, okay. Now, this light bulb looks like it's suffering from diabetes. Okay, forget about my circuit. This light bulb, let's also represent this light bulb as a resistor. So let's call it RL. Is that okay? Now, when we do this, we know that current, a certain amount of current is going to flow. And the voltage that this light bulb or this load is going to see, we can actually measure it across. So if we put a ground here, the voltage seen by this load, let's call it V out. Is that okay? And we can see it, we can measure it across it like this. Is that okay? Now, we are looking at, since the duty here is to move power from the source to the load, okay? We already established the fact that it is impossible to move 100% power source, it's impossible to move 100% from here to here. So if, let's say, we start with 100%, right, we may end up with 90% of the power transferred. The reason is that there are losses along the transmission line. Is that okay? There are losses along the transmission line. However, as engineers, we wouldn't like to be wasting the energy. So we want to find out the scenario or the instances or whatever configurations that we can set this circuit so that, yes, although we're going to have some losses, we would be able to transmit maximum power. Okay, so that is what we are looking at. We want to transmit maximum power from the source to the load. Okay, and in electronics, this is something we call maximum power transfer theorem. Okay, maximum power transfer theory. Is that okay? So I'm trying to let you understand because we will need the same concept in PCB design. Is that okay? So quickly, we are going to list out the various scenarios we can think of. Now, the first one that I want to talk about is assuming our load resistance or the load. So the bulb that we have put here has zero resistance. Okay, assuming its resistance is zero, what would happen? Okay, so let's analyze it. If this resistance, if the resistance is zero, then from maths or from the concept, the power of our circuit, the power transferred can be, or the power received by this, the load can be calculated either by as a product of current times voltage, okay, and the same thing can be expressed as I square product of the square of the current times the resistance. And the same thing can also be expressed as the square of the voltage over resistance. If you are interested, you can check out the mathematics, okay? Now, you can find all this from manipulation of the power and Ohm's law. So, straight by looking at this right from here, if our resistance RL is zero, then that shows that, yes, we are going to have current, all right, but then the resistance is going to be zero. That means you have 0 watts of power transfer. Nothing at all will be transferred. So I asked that, what does this physically represent? And Nikat answered that. So before then, I said, this means that if we should find the voltage drop across this load, whose resistance we have set to zero, then from Ohm's law, which says that the voltage drop will be current times voltage times resistance, the voltage that is going to drop in this scenario is going to be whatever current is flowing times zero resistance, which is actually 0 volts. Is that okay? So that means if we put our multimeter or ohmmeter at this point and measure, okay, if we measure between these points, we are going to get 0 volts at this point. Okay, we're going to get 0 volts. Okay, so that means this point is going to be 0 volts. So I asked, in what scenario, what does it physically mean to have a 0 volt at this point? Then Nikat actually answered right. It was perfect. That means this has been short circuited. Okay, so I further explained that yes, that is actually true. The only way we can have 0 volts while having something here is that we take a piece of conductor and connect it between here. If we do this, it's like we have bypassed this particular component. What is going to happen is that current will always take the path of minimum resistance. And in this case, that is going to be this path. That is what will create a situation we call short circuit. So this is a typical situation of a short circuit, okay? So in a short circuit situation, we are not going to have any power transfer. Take note, current is going to go waste, all right, but power is not going to be transferred. Why? Because power is the rate of doing work. Though current is moving, all right, there is no voltage across, and that means we have just shorted our battery. Don't do that in the house. Okay, so that's the first scenario that we have analyzed. Any questions on this before I proceed? So this is taking RL to be equal to 0 ohms. Okay, all right. Now scenario 2, we are trying to find what situation can we have maximum power transfer. So right now we've taken the extreme low. Let's also look at the extreme high. The extreme high situation will be when the resistance of the load is infinite. Okay, so we have an infinite ohm here. Okay, now if we have an infinite ohm here, you know what is going to happen? Let us pick it from this. Let us pick it from this. So if we have infinite ohm, yes, there's going to be voltage across anyway, but let's look at something. From power calculation, V squared over R, and take note, I'm choosing the various expressions to suit what I'm doing. Is that okay? Now, so this is a situation where we will have some value. So we have some value over here. but then now our resistance is infinity. What do you think this is going to give us? So we have a fixed value and a value for voltage, but we are dividing it by infinity. What do you think is going to give us? Yes, the mathematicians, tell us something. What do you think is going to be the result? If so, let me give you a clue. If I have 5 and I divide it by 50, what do I get?
Um,
Yes, okay, so answer. Go ahead. Go ahead.
yeah, your the power would be approximately zero since the resistance is.
Fantastic. That is brilliant. Okay. So you see, anytime you have two numbers divided, okay, whenever the denominator is way, 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 way greater than the numerator, you approach zero. So this thing approaches what zero. That means power will not be transferred in a scenario where we have an infinite resistance as a load. Now, physically, what would this mean? Under what circumstance can you think of an infinite load? A load with infinite resistance. Yes, any takers?
There's probably a break in the circuits.
Exactly. This can only happen if there is nothing. So let me get rid of this so that you don't confuse. So I use this to explain a concept. So let me take it away. Okay. So the only way that can happen is that there is actually no connection. Okay. There is no connection. Okay. There is no connection. So if there is no connection, then simply there's not going to be any current flow. Hence, again, when our resistance is infinite, our load resistance is infinite. In this scenario too, we will have 0 watts of power flowing. So you can see that in the extreme situations, that is the first one being zero resistance and the other being infinite resistance. In both cases, we are not going to have any power transfer. Is that okay? So this situation is where we have an opened circuit. Opened circuit. Okay. So let's take another scenario. Let's say this time our bulb's resistance, so which we labeled by RL. So our RL is equal to RTH. That is, our RL is equal to the resistance, the internal resistance of our source. Is that okay? So in that case, what is going to happen is that if you check this out, if the power, we can calculate the power as I want a simple way to approach this. Okay, let me approach it this way. So if we choose a situation where our RL equals to our RTH, then we can actually compute for the voltage drop across our load. Okay, all right, Elijah, go ahead. Let's call the voltage drop
So
across. Yeah, go ahead.
please, I want to ask,
Okay.
in this situation, what
Mm-hmm.
if you are using a load which has a specification of, let's say, 30 volts, but you have something like 2 volts running into it? How will you turn that to?
Already you know that's not going to work, right? You can if your load is requires more than your energy source, then you probably have to find a way to boost your power, your voltage. Okay, naturally that won't work. Okay, we are looking at situations where, so for instance, in this case, you have the voltage matching our the voltage requirements. Is that okay? So maybe I should have made that clear. We are looking at a situation where we have voltage matching. So our battery is probably 9 volts. Our load requires 9 volts. Okay. We want to see under what circumstance, what resistance of the load could make maximum power transferred. Is that okay? That's what we are talking about. I don't know if you're okay. Hello, Elijah. Are you okay?
Yes, sir.
Okay. So we are now looking at a situation where the resistance of our load is comparable to the internal resistance of our source. Is that okay? So in this case, yes, we are going to have power transferred and we can actually compute it. Okay. since this the voltage seen by the load will be the voltage here, we can compute V naught as VTH, which is the source voltage coming in. And if you look at this, we just have this resistance RTH and RL, they form a series circuit. Is that okay? So that means that RL would be RL divided by R. This is what we're going to get. Is that okay? This is what we're going to get. Now we said that RL is equal to RTH. So let's just make it R. Okay, so this is the definition. RL equals to RTH and we are representing it by R. That means that from here we can get something like VTH into R over now. RL is the same as RTH and we are calling both R. So that means this is going to give us what? 2R. I hope I'm not doing anything wrong. Okay, that's going to give us 2R. And you can see from here that this can cancel that, and immediately see that the voltage is going to be halved between them. Is that okay? The voltage is going to be halved. Now, the same current is going to pass through, so that means the power that will be transferred, if we use IV, is going to be okay, so the current that let's find the current first. The current that will be transferred, I, can also be computed as the voltage coming divided by the total resistance, which is going to be RL plus RTH. Okay, please follow so that you don't get lost on the screen because I'm typing random. I'm writing randomly on it. So follow. Is that okay? So that means that our total current that will be seen is going to be V over, since this and that are the same, we are going to get V over what? 2R, true of us. Please, if I make any mistake in the manipulation, draw my attention, okay? So power equals to VI. Our I is given by this, so that will be V over 2R times our voltage, which is also V over 2. Now, that means that we are going to get V times V to give us V squared. Let me write it here. We're going to get V times V giving us V squared, and then this giving us 4R2. Now, for the sake of time, so let me write it here. For the sake of time, I'm going to write this here for 4R. Yeah, I'm going to put this somewhere. So this is the relation that this is the maximum power that can be transferred. Now you can do your own analysis and check, okay, what if RL is like 2 times RTH? What if RL is like half of RTH? And come up with the expression. Now, if you check the expressions, you will realize that under all those circumstances, there will be no instance where you get maximum power higher than this. Is that okay? So what this physically means is that for you to be able to transfer power, maximum power from any source to any load, the resistance of that load should be comparable to the resistance, the internal resistance of your source. That is what these things mean, okay? So when we go to the PCB session, you'll be hearing about impedance matching. Impedance matching. I already told you that impedance represents resistance, inductive reactance, capacitive reactance. Is that okay? They are just all oppositions to the flow of energy. Okay, so when you hear of impedance matching, just think about this, that we are trying to do some configurations so that we can get maximum energy transfer along whatever we are talking about. Is that okay? So you can try this out. Pick situations where R is twice RTH, R is half RTH. You will see that none of them will be comparable to this. This is the maximum power. This is the configuration that will give you a maximum power. And practically or physically, it means that if my internal resistance is, let's say, 20 ohm, then the load should also have a resistance of 20 ohm. If this happens, okay, if this happens, then we say that impedance has been matched. Impedance has been matched. So it simply means that the source impedance is the same as the load impedance. And when this happens, you have maximum power being what? Transferred. Please, is this okay with everyone? If you have any questions, bring it up
Please,
before.
can you please that again, please? Just
Which of them do
as
you which of them do you mean, please?
I mean, why citing the example of
Okay,
R
okay.
raised
So what
to
I mean is this. You remember we said we can model a source because of the non-idealities in our power source. We can model it as an energy source with an internal resistance. Okay, so the whole concept about maximum power transfer is that for you to be able to transfer maximum power, whose formula we have determined to be this, okay, which formula you have determined to be this, then the if you are using a battery, the internal resistance of your battery should be the same as the internal resistance of whatever load you are connecting to it. Is that okay? So if your internal resistance is, let's say, 20 ohm, which is actually extreme, then your load resistance should also be around 20 ohm in order for maximum power to be transferred. Okay, so that means that if my internal resistance, the internal resistance of the battery is 20, and my load resistance is, let's say, 50 ohm, I won't have maximum power transfer. The same way, if this is also less, let's say 10 over here, I won't have maximum power transfer. And I said that you can actually cross-check this by setting a situation where RL is maybe twice RTH, a situation where RL is half of RTH. In all those things, you realize that the values that you get for the power transfer will be less than this, what you have over here. Okay, I don't know if that answers your question. Okay, please, any other question? Any other question? So the whole is if you couldn't follow the mathematics and all that I was trying to do, the whole thing I need you to take is that for maximum energy or the maximum energy that we can ever move from this source to this load would occur when the internal resistance of this source is the same as the resistance of the load. That's all. Is that okay? But yes, I have people who are curious mathematically. That's why I had to prove these things. So please, if you have any questions, bring it up so that we can continue. Oh, I just confused you. Okay, so
You did great. I really appreciate that.
thank you, sir. Thank you, sir. So we've also already talked about the type of impedance. Okay, so for the sake of those who weren't here, can I wipe this clean? Can I wipe it clean? Okay, so please, somebody should buy me a supercomputer. Okay, contact Elon Musk or something. Get me a super. Get me a supercomputer. This thing is really annoying me. Okay, so let's continue. Okay, let's continue. We still move anyway. All right. So the next thing that I want you to understand is the concept of impedance. Okay. So impedance is a general term to opposition to the a general term, is it off or to? Forget about that. To the flow of energy, okay, flow of energy, okay, impedance, okay. Now, when we take impedance, we can actually talk about two things. I'm going to talk about two things first, then we'll start run. So most of you are aware of resistance, okay. So resistance is one of the children of impedance. But we also have another thing called reactance. Okay? And reactance, take reactance as a form of resistance by components like capacitors and inductors. Is that okay? Capacitors and inductors. If you remember, we said that a capacitor resists the flow of a change in voltage. Sorry, voltage doesn't flow. We said that capacitors resist a change in what? Voltage. Okay? Inductors resist a change in current. Okay? And the way they work, that's how we define those things is what we call reactance. So when we talk of reactance, which we usually represent by X, impedance by R, reactance, we have two types. We have what we call the capacitive reactance, which, as the name implies, would be due to capacitors and is symbolized by XC. And then we have inductive reactance. So inductive reactance, okay, which is XL. Generally, we use L to represent inductors and C for capacitors. Okay, so all these things, one, two, three, that together we call them what? Impedance. Is that okay? But then these things don't usually always come into play at the same time. Is that okay? And I'm going to explain that quickly. Now, please, everything I'm talking about right now here is required for the things I'll be explaining during the PCB design. So pay attention. Okay. So when you are dealing with DC stuff, like maybe most of you have done before, connecting a battery to a light bulb, connecting a battery to a light bulb. Okay, such situations you are doing this, and usually when we talk about DC, the whole idea is frequency is equal to zero. Is that okay? Now, the moment we put frequency to be zero, I think if I remember correctly, this guy is expressed as I think 1/, is it a square root? Is it 2 pi something? Please, if you remember, draw my attention to it. There is a relation for it.
1/2 pi
Yeah, 2 pi
f.
FC. Thank you. 2 pi FC. Okay. So you see this F here, and this one is 2 pi, I think FL, something like that, right? So you see that they have a frequency component in them. So meaning if we set frequency to zero, then capacitive inductance, capacitive reactance goes to zero, inductive reactance goes to zero, and the system just becomes resistive. Is that okay? And yesterday we saw that for resistance is something, it's a property in the material itself. Is that okay? So resistance is not actually affected by the frequency. But in a situation where our frequency is not zero, then these guys also come into play. So mostly you hear of resistance because mostly you are dealing with zero frequency applications. Is that okay? So keep this in your mind that when you hear of impedance, it's about these three things. Now, in a situation where I want to talk about either of them, I'll mention them directly. Please, any questions on this? Any questions on this? Understand this though, because when we move ahead and I'm explaining the concepts in PCB, if you don't get these things, you would be lost. Is that okay? All right. So if this is okay, then now let's go into PCB so that I can explain something. Okay. Please, any questions? Any questions? Let me shut this thing down. Okay, I think we can still stay here as I explain the PCB stuff. So now we are going into PCB. Everything I'm coming to talk about, we will use it in the PCB, okay? So let's clear this. Okay, let's say we have a piece of copper, or when they are creating a PCB, for instance, in our case, we are ordering for a two-layer PCB. Is that okay? So what they do is what they will do is this. There is a material they call the core. Okay, so they take this core and this core already. Come on. So if let's say this is the PCB, the piece of PCB core, okay, and usually it has a height. Okay, it has a height, a thickness. That's how we do call it. Okay, forgive my Azonto diagram. Okay, then what they do is they fill this place they fill the top and bottom with copper. Is that okay? So copper on the top, copper on the top, and on the bottom too. Is that okay? Now this copper, they actually know the thickness of the copper. Usually you hear of 0.5 ounce for internal layers, and I'll explain what we mean by internal layers. You can hear of 1 ounce for external layers, okay? But in situations where you are dealing with current heavy applications, you can actually request for 2 ounce, okay, of copper thickness. Okay, so take note of this, and let me ask you something. If I have copper here on the bottom, right? In essence, by default, what do you think I have created? So I have a piece of metal with a thickness, and on top of it I have copper, and on the bottom I have copper. What component does this resemble? What component does this resemble? Yes. I have a piece of copper.
Becomes a capacitor, I think.
Fantastic. In fact, I would have said clap for him, but we are online. Okay. So by default, the moment you pick this core, so this is the PCB core, the core material. Okay. The moment you pick this, you are in essence holding a capacitor, just a parallel plate capacitor. Okay, because in creating a parallel plate capacitor, we take two metal plates and put a distance between them. Now this distance could be filled with air or a dielectric material. Okay, and I think yesterday, dielectric material, I explained that dielectric materials are just insulators. Is that okay? So the copper board by default is acting like a parallel plate capacitor. Is that okay? So if we should pump positive charges on top and negative charges, we have in essence created a parallel plate capacitor. Okay. Now put this in your mind. We'll come back to this. Now let me undo, so that we have just our board over there. I just hope I can finish this concept. Okay. So this is the copper plate. They have what? Loading board content. What just happened? Can I cancel this? Thank you. Okay. So two things. Okay. Now I'm going to redraw this as this. So this is the top layer. Okay. This is the bottom layer. This is the bottom layer. Okay, we try to fill it up. Then there is a material in between. I think usually the material would be something called FR4. Okay, fire retardant 4. Okay, so usually the core here will be FR4, which is the substrate on which the copper has been plated. Okay, so let's say we have FR4. So we have a distance, a distance that we can actually measure. Let's call it D between these two plates. Okay, and we have copper here, copper there. Now, if we take this board and we pour, so assuming we tie this bottom copper to ground, is that okay? We tie this bottom copper to ground, and then route any piece of copper. So what I've done over here is like I have routed some piece of copper on the top layer like that. Oh, come on. I've routed this on the top layer like this. Okay, so this is a PCB trace routed on the top layer like that, right? So you are what I'm doing here is like just the end view of it. Okay, so let me label this. This is a trace. Okay. Now, whenever you have a trace that is exposed, one side of it is exposed to air, right? And the downside is exposed to a plane, a power plane, usually ground. We call this trace a microstrip. Microstrip. Okay. Now, in our case, we are going to deal with just a two-layer board. But there are also instances where you can have multi-layer boards. So let me sketch a typical example. So let's say we want a 4-layer board. What they will do is first they'll take the core, okay, and the core already comes with the uh, cured FR4 or core material, okay. So this, we have copper here, we have copper there. Then they'll put a material called prepreg, okay, call it prepreg. They'll put it on top here as a form of glue. So they'll put here, and then they'll put it over here too. So this red thing is the prepreg, okay. You can check on details, sorry, you can read about them online, okay. Then now they put on top of it would be another copper layer, okay. So I put another copper layer here and another copper layer here, and then that forms a 4-layer board. Is that okay? So take note, if my copper trace is on a top layer, on a top or bottom layer like this, okay, and it is referencing a power plane. So it's referencing this ground plane here. It's referencing this ground plane, okay. So referencing means beneath it is this ground plane. We call this a microstrip. A microstrip, okay. So it's a trace, it's a copper trace like we have here, but it's given the special name a microstrip. However, if we actually design this, for instance, we design the trace in an internal layer like this third layer here, so that it is sandwiched between this plane, and let's say this plane is also tied to ground, and that plane, you see, it is enclosed between two copper plates. We call this a strip line. A strip line, okay. And the reason I'm talking about it will become clear when we start routing. So take note, if you hear me mentioning microstrip, it means a trace that is exposed to air and also with a plane beneath it. A strip line is a trace that is enclosed between two planes. Is that okay? Please, any question up to this point? Any question up to this point? Yeah, right.
Please, can you go over the microstrip?
Okay.
The difference
Just
between the
to be
microstrip.
clear, okay. So I'll go over. Christine, what's your question too? So that I'll answer both of them together.
So you want to mean the first one whereby it has the FR4 in between. It is a single layer and the other one is a double layer.
Okay, so actually, if we want a single layer, that would not have. This is actually a double layer or 2-layer because we have top and bottom. Okay. Now here we have 1, 2, 3, 4. So this is what we call a 4-layer. If you are talking about a single layer, then that will be. Let me draw this. So for a single layer, we will have some substrate material over here. Okay, and then we will have our copper just at the bottom. That's what we will call a single layer. Is that okay? So there is no copper on top. We have it just at the bottom. So this is a single layer, single. This is double, and this is 4-layer, okay. And take note, you can have so many layers, even 64 layers. I think a typical iPhone should have around 22 layers or something, okay. Yeah, so it depends on the nature of whatever is being developed. You can have multiple layers. Yeah. Does that answer your question?
Yes, it does.
Okay.
Thank you.
So the one who asked about the microstrip. So say we are creating let's say we are creating this double layer board, right? And then I pour ground on this bottom side here, and I put a certain route, a trace on the top side, okay, such that this trace is actually sandwiched between air on top of it and this plane. Then it is called a microstrip, okay. But in a situation where the trace is between two planes, like we have here, okay, so it's rather than the tail layer, so it is between that and that. We call it a strip line. Please, is it okay?
Yes, please. Thank you.
Okay, good. Now, the next concept that I want to talk about is what we call transmission line. Now, I know those who have been following maybe Zach or some other PCB evangelist, you would hear of transmission lines. Okay, transmission line. Now, this transmission line generally in engineering, okay, this is a concept that is borrowed into PCB. Transmission line is take a situation where you have to carry maybe signal over a very long distance. Is that okay? If you don't safeguard this signal, it will end up picking noise on the ground, on the way, and a whole lot. So a transmission line is actually a special a way we actually, let me see if I can get some images to show you. Oh, okay, okay. So a transmission line is just a special way, or a cable. It's a special cable that we use to transmit energy or electromagnetic waves, so that it feels containerized. Is that okay? The waves feels containerized. So uh, once the wave is being transferred, we have minimum losses. Okay, so sometimes you hear of coaxial cables and that. So you have the main line doing the transmission, then you have some other conductor encircling it, so that the EM wave actually just stays within. It doesn't spill out of this particular it doesn't spill out of the container or the cage. Okay, so we call these things waveguard. Okay, so if you want, check on something called Faraday's cage. Okay, those who have done physics before, you understand this. Faraday's cage. So this metal enclosure here prevents the EMF from moving out, and it also prevents some from entering. Is that okay? But of course, it wouldn't be 100% efficient, so there will be losses. Is that okay? So anytime we have to transmit energy or some EM waves over a very long distance, then we employ the concept of transmission line, where the energy is transmitted through things called waveguards and something. So you can check on coaxial cables. Okay, coaxial cables. Okay, so that's the entire concept. So in PCB design too, sometimes in fact, oftentimes you want the energy, and take note, the trace carries energy. The trace serves as a waveguard to direct where the energy is moving. The energy itself doesn't flow in the trace. The energy flows in the spaces around the trace. Take note of this. Energy doesn't flow. So you can get electrons flowing as a reaction to the movement of the energy, but the energy itself flows in the spaces. Okay, so for instance, if we take this double-sided, the energy is going to be contained beneath here, within. Let me draw that with a different color. So under the trace or within the PC, the energy will be contained here. But in air, because there is nothing to restrict it. Now, take note, the energy cannot travel through a metal. Okay, so if I have a solid plane over here, I can't have the energy spilling off in that direction. It can't. And the energy we are talking about is made up of electric field and magnetic field. Is that okay? But when you come to the side of the trace that is in the air, the magnetic field would be all over. Okay, the electric field would be also spilling all over it. Is that okay? Good. So mostly we want to control through this. Okay, we want to contain this as much as possible, because if this electromagnetic spillage, if I may call it, happens, if there happens to be another trace here which is also transmitting very sensitive signal, these electromagnetic fields that are coming out here can interfere with this and cause a situation called crosstalk. Is that okay? Crosstalk. Now, according to Faraday's law, sorry, I have to be technical some way, but for the sake of those who don't have physics background, please just bear with us. I will still try and explain things in a layman's term as possible. But I mean, for the sake of those who also like these technicalities, okay. According to Faraday's law, anytime there is a changing electric field, right? When there is a changing electric field, it can induce a magnetic field. Take note of that. And these things are also summarized in Maxwell's equation. You can check on them. So when we have such a field spilling over, and this field happens to be changing, okay, in a situation like a high frequency application, then it is going to generate energy in this, though we don't want to have energy in it. Okay, so assuming this line is probably a sensor line which is reading some temperature, okay, which is reading some temperature. When you record this temperature, because of the interference by this, you realize that your temperature reading is so not stable. Is that okay? Because this guy here is having influence on it. So in PCB, we want to reduce this thing as much as possible. Is that okay? One way you can do that, we already know that this, what do we call it? The EM wave cannot travel through a metal. So it means that if I create a trace in an internal layer, and I have a metal over it and a metal, then this EM wave, one way or the other, becomes what? Contained. Is that okay? One way or the other becomes contained. Okay. Now, anytime we are working, you see, when we draw just a single trace, anything on the anything serving as a connection on a PCB is a trace. Okay, it's by default a trace. Okay, but a trace gets our attention when it qualifies as a transmission line. A trace will get our attention when it qualifies as a transmission line. Now, when does a trace become a transmission line? A trace becomes a transmission line when its length is relatively longer compared to the signal that it has to carry. Okay. Now, there is a divide. There is some contention around these things among designers, as in among engineers, as in what length should we actually start recognizing this. Okay, but I'm going to explain things according to my understanding so that you can also cross-check later. Okay, so the length here, what should determine the length, or at what length should we consider a trace as a transmission line? Is that okay? So the thing is, the moment we begin to treat a trace as a transmission line, then certain things have to be done, like anything that we can do to contain the field, the return path, and all those kind of stuff, the impedance and everything. Okay, so let me use a scenario. Let's say you have a tortoise, okay, and I hope you all know what a tortoise is. So we have a tortoise. Take it as a turtle, okay? I have a tortoise over here. And this tortoise is supposed to move this distance, okay? Now, this distance is, let's take it as 1 meter. The tortoise is supposed to move 1 meter. Is that okay? And we also have a hare or a cheetah. Let's use a cheetah. And by cheetah, I don't mean a man who cheats on the girlfriend. Okay, so we have a cheetah, which is also, I think, the fastest animal or something. Okay. Now, the cheetah can actually run very, very fast. I have forgotten how much its top speed, but let's assume that this cheetah this cheetah too is supposed to run this 1 meter, right? But the cheetah can actually, the tortoise can complete this 1 meter in, let's say, 1 hour, or 1 hour will be too much, let's say in 10 seconds. Okay. But the cheetah can actually run this 1 meter in a second. Please, are you following? Please, are you following? Are you there? I need your
Yes,
response.
yes.
Okay. So you see, to this tortoise, okay, this is quite a lot of distance to travel, true or false? To the tortoise, it's quite a distance to travel. But you see, to the
It's true.
cheetah, it will almost feel like the cheetah never moved, because by just a blink of an eye, the cheetah would have moved from here to here. So it will be like the cheetah never moved at all. Is that okay? So I'm trying to create this analogy to be able to see if I can make you understand when we consider these things. Uh, we consider the transmission line something, a trace as a transmission line. Okay. So to consider this, I think it has to deal with the frequency of the signal that you are transmitting. Is that okay? If the frequency is so fast, okay, like the cheetah in this case, then it will be like, you see, it actually takes some time. Let's say I have a voltage here and this is my time here. When I switch on a digital signal, for instance, it takes some time to actually attain it full. So let's say this is supposed to be, let's say, 2 volts, right? It takes some time to actually reach this 2 volt, and that is what in electronic sense we may call it the rise time. Let's call that TR, rise time. Now usually we consider it as like when we have 10% of it to about 90% of it. Is that okay? So it is all about this rise time. Okay, so if the rise time of your signal is such that it's this distance, it doesn't even feel like it is moving at all, then you don't actually have to worry, because you are not going to lose any power through your transmission. Is that okay? So over here you can conveniently route the thing as a trace. Okay. But in a situation where the rise time is comparable, and I think usually when they do the analysis, if do I remember this carefully, I think Zach has a very beautiful tutorial on this thing. Okay, Zach has a very beautiful tutorial. But let's look at a situation where we know this cheetah could complete 1 meter in 1 second. Let's look at a situation where the cheetah has to complete 100 meters or 10 meters. Is that okay? In this case, then we could actually see the cheetah move. So we have to be, we cannot just ignore the fact that, oh, the cheetah has quite a distance to move through. Is that okay? So what I'm trying to draw, associate this analogy to is that when the rise time, the ratio of the rise time compared to the length it has to travel, okay, and you can actually calculate if you know the frequency of the signal or the velocity of the signal. So let's say the velocity of the signal is v and the rise time is tr. You know, when we multiply velocity by time, what do we get? We get distance, right? So let's call that distance lr, right? So if the lr, which is the distance that the signal would have traveled before achieving its maximum, its rise time, compared to the length of the signal, if it's the difference is so much, then this becomes critical. In that case, you have to start treating the trace as what? As a transmission line, because you have to now pay attention to the losses that can happen, right? But in a situation where it is almost like the signal is not moving, get me water. It's almost like the signal is not moving, okay? Then you can just treat it as a normal trace, because no matter what, you would get your energy transferred from your input to your output. Is that okay? So in simple terms, I would you can define a transmission line as a long trace, a long PCB what trace. Is that okay? So the long, as in the length, what you should consider as the length, that is what I'm trying to say, that before, what the things that you should probably look at when you are considering what to define as a long trace is check the frequency or the rise time of the signal that you have to transmit. Is that okay? That should give you a clue about what trace you should consider as a transmission line. So take care of losses, impedance, reflections, and all that kind of thing. Please, any questions on this? Any questions on this? Zach has a very beautiful yeah, I think he has a very beautiful thing where he explains with the mathematics. So those who are actually interested in the details, you can check his tutorial on Altium Academy. Okay, but this is like about it. Okay, so a trace is something that we don't have to worry about energy losses usually. Okay, in simple terms, if you want to treat something as a trace, yeah, we can just connect it without worrying about energy losses. But if there is a potential for energy loss in a signal that we are transmitting, then we have to treat that trace as a transmission line. And by treating it as a transmission line, we have to be careful about impedance matching. We have to be careful about anything that can lead to losses on these lines. All right, any questions on this? I want to start the routing before this session ends. Any questions on this? Please, any questions on this? Any questions on this? Are you guys there, or my network has disconnected me? Any questions on this?
We're here.
Please, are you
You did.
confused or you are confused? Which is which? Don't worry, if you really don't get it here, probably when we start doing the actual layout, you begin to understand it. I just want to explain the concept before we go in there. Okay, so any questions? Any questions?
Okay, so I have a question.
Okay.
So by the length of the by the length, you mean the length of the trace
Yes,
from
the length of the
one
trace.
terminal to another, right?
The length of the trace. That's the trace that is actually conducting the energy from the source to where it's its destination. That's what I'm talking about.
Okay, so from the source to is this
Not source. So take note here. If you say source, it could mean the source of the entire circuit. No. You see, for instance,
Okay.
if you are sending a signal from Arduino digital pin to maybe a diode, right? That trace that links the digital pin to the diode. That's what I'm talking about. So the point where the Arduino switches the signal, that's the input, and the point where the signal reaches the diode, that's the output. Okay, so just that length, okay, not like the entirety of the board.
Oh, okay, okay.
Yeah.
I think I understand.
Okay. Please, any other question? There is one more thing I want to explain before we go into the PCB. Any other questions? Any other questions? Yeah, David. Yeah, go on. David, you can go on.
Okay, sir.
Yeah.
So yeah, my question is based on the impedance you explained the other time.
Yeah.
Though you explained it based on the routing, but I'm talking. My question goes for the components. You know, we have some inductive components like inductors and their placement in the PCB board. I mean the circuit.
Yeah.
Does it have any effect, or you can just place anyhow based on?
Okay.
I
So
don't know if you can.
yeah. So mostly, okay. We actually have a whole concept, something called high-speed design, right? Which we usually do when you are dealing with very fast switching of circuit, high frequency circuit. Okay, you cannot just place these components anyhow. Okay, if you were part of our previous when we're talking about capacitors and I was talking about decoupling and all that, you see the PCB. Okay, I'll get there very soon. The PCB trace, okay, or any inductor, any conductor, okay, actually has an inductance property. Okay, just that for, let's say, a normal PCB trace, usually the one that is quite obvious is the resistive, right? But then, depending on the frequency you are working, you could have the inductive impedance coming up, okay? The inductive impedance playing a role and the capacitive impedance to playing a role. Okay, so if you don't actually place these things, well, for instance, if you are placing a decoupling capacitor and you're supposed to place it very close to the IC as possible. The more you move it away from the IC, the more you are introducing inductive impedance, you are introducing inductance into your path. Is that okay? And they will become parasitic. They'll end up having effect on your signal. Is that okay? So you cannot just place components anyhow. Okay, you cannot just play. If you weren't part of that tutorial, please check the previous tutorials. I talked about these things. Okay.
Okay.
All right. Please, any other question? I want to do another thing. Uh, So we've been talking about impedance, we've been talking about transmission line. Okay. So what are some of the things that I have to note when I am routing, when you are routing a transmission line? Okay. Okay. So what I'm going to talk about right now are situations where or what causes the general on a PCB, how do we get the impedance? What actually dictates the impedance on a PCB? Okay. Now, once again, I'm going to draw in. I'm going to draw in an end view. Okay. So this is the take this as the material. Okay, and then on top here. No, let me do this instead. So let me color. This is the board. Okay. Okay, so let me draw it again. So this is the board, the physical board, okay? And then that is the core. So since we are dealing with a two-layer, I will be spending much of my explanations will be on that. Okay? So this is the internal layer of our the double-sided board. And on top here we have copper. So we're going to route our traces on this copper. Let me just try and see if I can make it, yeah, just a single line, something like that. Okay. Just trying so much to get it. Okay, right. Okay. And let me also try and see if we can have a 3D view like that. Okay, something like this. Okay, so copper on top, copper on the bottom. Okay, when I have and I put a trace on this top side like this, let's say I have a trace moving from here to there like that. Okay, so this is a copper trace. Okay, and let's say that there is a ground plane beneath. Okay, so in between the trace we have capacitance. Okay, so there will be capacitance between I already mentioned that. Okay, there will be capacitance. Now, in the trace itself, it's made of copper. There will be resistance. Is that okay? And also, there would be inductance L in the trace. Is that okay? So if we take this as a transmission line, we can actually model it as some having a series resistance and a series uh, inductance, and then I think there is another third parameter that is usually labeled G. I've forgotten it a bit. Then there will also be capacitance over here. Is that okay? Then the signal will count. So let's say this is our signal source. Okay, this is our signal source. Okay. So what determines the overall impedance? And remember, I've mentioned that impedance is made up of three things: resistance, capacitive reactance, capacitive or inductance. What actually determines this when you are dealing with a non-zero frequency application is usually the inductance, which we usually call the characteristic inductance and label it as L naught, and the capacitance here. Okay, so these two values, C0 and L0, they determine the overall impedance. Usually the resistance aspect doesn't play much role when you are dealing with transmission lines. Okay, they don't play much role when you are dealing with transmission line. Okay, so this inductance is actually the inductance L naught is actually also it's not much of a variable because whatever it is quite tied to the trace itself. Is that okay? But the thing that actually has much variation or that varies much or we can actually tune to check to determine the final impedance that we come up with. It's usually this. Okay, so the board, remember, capacitance. So if we manage to tune this board thickness and also the cross sectional, the width, okay, the width of this trace, if you're able to check these things, I think there is a relation between capacitance and surface area. If not something like this, okay, somebody can cross check for me. There should be a relation like this. Okay, so that means that if that is my memory serves me right, then by adjusting the width of this trace and the distance of the PC, the distance of separation of the PC, we can actually adjust the capacitance, right? And since the capacitance plays part in the overall impedance of the board, that means we can adjust it by adjusting these parameters. Is that okay? So whenever we are drawing transmission lines on a PCB board, these are some of the things we will be playing with. So you will hear of things like the distance to the, how do I call it? Clearance. You'll be hearing about things like clearance, trace width, trace length. I mean, I'll go over these things when we start routing, okay? But things that I need you to take note. There are situations where you could have changes in impedance, okay? And let's say I have a trace of this width coming in, and then I by some magical means change the width of this tree. So it started with one and it ended with zero. If such a thing happens, changing from this dimension to this dimension actually changes the impedance. Is that okay? It changes the impedance. Also, if I have a trace coming in thick and then I make it smaller at the other end like this, again, you would have a change in impedance. Now, these things are not, you are supposed to avoid these things, especially this second one, okay? Now, in the case of this second one, physically, take it as you have water coming from a smaller pipe and it's discharging itself into a bigger pipe. Is that okay? You realize that you won't have a situation where some of the water is rushing back into this pipe, okay? Because the space here is enough to empty everything to contain the water coming in. However, in this situation, take it as you are pouring water from a jar or some bottle, you see there will be some form of turbulence at the bottleneck, okay? And you have part of the water coming out because the amount coming in here all cannot pass at the same time. Now, whenever this thing happens, we call something reflection. We got something reflection, okay? Now, for this situation, the reflection tends to be positive, okay? You get reflections, all right, it tends to be positive and it actually adds up to the incoming signal. But then, in this situation, the reflection that occurs becomes negative, and what happens is that it goes back to subtract from the energy of the incoming signal. So if you do something like this, you end up with a reduced signal strength or energy. You end up with a reduced energy. So when you are routing, avoid these things. You start with a bigger trace and end with a smaller trace. Ideally, let your traces go straight, okay, without changing width throughout its travel. Is that okay? And I'll be demonstrating these things on the in KeyCard. Okay. So these are some of the things that you should always try to avoid, because if you do them, you are going to have changes. Your impedances what changing. Is that okay? All right. Any questions on this? Any questions on this? Now, all the things I'm talking about, there are actually mathematical expressions for them, but I'm not going to talk about those things. Where's my water? I'm not going to talk about it. Like I said, check Zach's tutorial, and if you're interested in the mathematics, you can check them out. Now, the last thing I'm going to talk about is the concept of differential pairs. Okay, the concept of differential pairs. What do you know about differential pairs? Do you know of it? Okay, so right, yeah, your question.
I want to know if the EMF of another signal, if it's possible for the EMF of another signal to affect another signal when those traces intersect, let's say from the top layer and then the bottom layer, if it's possible.
So it actually depends on what you call intersect. Okay. So scenario one, if we have two layers lying side by side, uh, if you have two layers going side by side like this, okay, and one layer is carrying high frequency signals, okay, we usually call it the aggressor. It's an aggressor, okay. It carries high frequency signals. It can actually induce energy into this, okay, and that's what we call crosstalk, okay. Now, one thing that you should also remember is that this EM waves that we have energy we are talking about, it cannot penetrate another, it can't go through a metal. Is that okay? So for what you are saying, it depends on where your signals are. So let's say I have a two-sided board like this, and I have a signal on top here, okay, and I have another signal over here too. Okay, take note. I said initially that if I have a ground plane over here, this signal is going to couple with this. Okay, it's going to couple. So yes, because of this coupling, there can be cross-talking. So usually what you do is that, let me say, if this is the surface area and the top signal is going this way, you route them orthogonally. Okay, so the signal going down, usually it's advisable you route it this way. Don't route it to be parallel to the aggressor, else there is a possibility of coupling. However, if let's say this is a four-layer board and then the other signal you are talking about is down here, you see, remember these layers represent copper plates and the energy cannot move from here to affect this. So you are safe in this case. I don't know if I've answered your question.
Yes, yes, you've answered the
Okay.
question. But I would like you to clarify something else for the
Okay.
cross coupling. So that's when the EMF of the other trace induces energy in the other trace, right?
Exactly. When the EMF starts, it has to enter, it has to terminate somewhere. Is that okay? So whatever surface it gets, it can induce charges on it.
Okay.
Okay, it can induce. And if it also happens to be a varying signal, then according to Faraday's law, when we have a changing electric field, it can induce what? Current in another,
Okay.
or it can induce EMF in another device. That's the same concept for transformers.
Okay. 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 Thank you very much.
You're welcome. Please, any other question? Uh, oh, wow. Okay. At least if I'm able to finish with all the concepts and then we start the routing session, I think it's okay, because these understandings are the things I'll be applying when I'm doing the routing. Is that okay? Now, the last thing I want to talk about, unless there is a question, please, if there's any question. The last thing I want to talk about is the concept of differential pairs or differential signals. Okay. So again, let's select this and delete them. Now, what do you know about differential pairs? Those of you who have heard of it or used it before, what do you know about differential pairs? What do you know about it? All right, Christine, yes.
I remember when we were creating, I think it was the library or the circuit. You mentioned the D positive and the D negative, and you said they were differential pairs. I went to
Okay.
check on it, and I
Mhm.
found out that on opposite polarity, the signal carried by one wire is the same as the other signal carried by the other
Okay,
wire.
okay. Very good. Very good job that you went to check on it. That's very good. Any other? Any other? What do you know about differential pairs? And then, oh, my eyes are very heavy. Okay, so any other? What do you know about differential pairs? Differential pairs. Have you heard about it? Where did you hear of them, or where did you see them being used? Okay. Yeah, Chris. Chris, go ahead.
Yeah, I think I've. Can you hear me?
Yes, please.
Yeah, I think I've heard about it. I think when I was trying to learn KiCad newly, and the guy was trying to route USB parts,
Mm-hmm.
talked about differential pairs, but I can't really remember the concept very well. But I know he was talking about differential pairs when he was trying to route the USB.
Okay. 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 That's cool. That's cool. All right. Okay. So quickly, I'm just going to touch on the surfaces of differential pairs. Okay. You can check on. There are tons of tutorials on Altium Academy and other places that you can check. Okay. Whew. Let's say we want to transmit a signal from point A to point B. Okay. This point A and that is point B. We want to transmit a certain signal. Now, this signal is very sensitive, and anywhere within this environment, okay, there is a possibility of picking up noise. Okay, so if I transmit this directly like that, in fact, let me use realistic. So I have, as people were suggesting, let's say I have a PC here, and my PC, and I have my USB cable connected to it like that. Okay, I'm transmitting. I'm communicating between this USB cable and let's say my Arduino. Okay, my Arduino here. Just an analogy. You see, where this thing is, this cable passes, there could be noise all over. And by noise, I mean things that could end up causing fluctuations on our signal. Is that okay? Great. So in a situation where, let's say, this is our source, SRC, this is our destination, and we use just a single cable to transmit this. So let's say the signal is at 2 volts. Is that okay? When or if something happens in the environment and maybe some fluctuations or some aggressive signal somewhere causes some interference on our signal line, it could actually inject voltage on our signal. So let's say this voltage is about one volt. I'm just overestimating here. This means that at our receiving end, this is now going to receive 3 volts. Okay, when this pipe finally gets here, we're going to receive 3 volts. In other sense, if this signal that superimposed on our transmission line rather subtracted, then we will end up receiving 1 volt over here. Sorry, 1 volt at the receiving end. That means the signal has been distorted. Okay, this is corruption. Okay, because if this receiver actually treats any signal from 1 volt to 0 as a low, then it is going to treat the signal as 0. Meanwhile, we actually transmitted a 1, so that will create a distortion. Okay. All right. So in differential pair, the concept is this: instead of using one transmission line to transmit the signal, we rather use two lines to transmit that signal. Okay, so take note, the D plus and D minus signals, they are actually parts of the same signal. Okay, these are not two different signals. No. When we are using the differential pair, we just want to transmit a signal, and just one signal, but we want to make it immune to noise in the environment. So instead of transmitting it over one transmission line, we rather choose to do it over two. Now, this is how we do it. Okay, the devices that are transmitting the differential pair, internally they split the signal. From that signal they generate. So let me probably draw a graph over here, see if I can use it. So let's say we have voltage here and we have time here, right? A voltage here, we have time here. So what happens is that, let's say the device is supposed to transmit at something like 2 volts. Is that okay? So it could transmit the signal at 2 volts like that. Okay, but that means the signal will be prone to noise, as I've already explained. So what they do is, instead of 2 volts, they will split this signal into +1 and -1 volts. Is that okay? +1 volt and -1 volt. Then transmit that and also transmit that. Okay. Now, one thing that you need to know is that these signals must start and arrive at the same time. And I'll explain why. So when you do this, you pass the positive 1 volt through one of the cables. So let's say this is the one taking the positive volts. And then you transmit the negative volts through the other cable. Is that okay? Now, another thing you do is you make sure these traces are very close to each other, so that anytime there is any electromagnetic interference or there is any noise affecting them, the noise is going to affect them equally. Okay, the noise is going to affect them what? Equally. Now, that is also very important. In a situation where the noise affects one more than the other, then the whole idea of differential pair will be defeated. Okay, so you need the noise or whatever aggression is happening to happen to them equally and also at the same spot. Okay, so let's assume that this noise is affecting them equally. Then on this volt, let's say the noise introduces a 5 millivolt signal. Since they are all being affected equally, so the noise is going to raise this by 5. So is it going to raise this by what? 5 millivolts. Is that okay? But take note, this is a negative signal. So increasing it means you rather become less negative. Is that okay? So in the end of everything, when I still measure the difference in voltage between these 2 points, I am going to get my 2 volts difference. And it will just be as if this noise never happened at all. Okay? So we say that when we do this, we say that the system has been able to reject what we call common mode noise. Common mode what noise. So if you talk about common mode noise, that's what I'm explaining here. when the noise is able to affect the two signals the same way and your system is able to reject them. So you see here, though there has been noise, all right, but then the noise increased this, it increased this and that, right? So let's say this the level will come to, since this is 5 millivolt, that means that this would reduce by, since it's negative, if I have -1, okay, plus -1 plus 5 millivolts is going to give me something lesser. Is that okay? Something lesser. But then 1 volt plus 5 millivolts is going to give me something greater. Is that okay? So in the end, since the IC or whatever device at the other end is rather checking the voltage differences, the the signal that was introduced, this 5 millivolt that was superimposed without our consent, the noise gets cancelled out because we are in effect dealing with the difference. And since it's the difference, the signal, the noise doesn't even show up. So that's why we say if we do differential pair on signals that are very sensitive. And by doing differential pairs, we are able to reject common mode noise. Is that okay? So that means that so far as the traces are being affected the same way, our signal remains on now what word do I want? Our signal is not affected. Is that okay? It goes through, the receiver can receive it and it is going to measure 2 volts at exactly 2 volts as we intended to transmit. Yeah, Chris, your question.
Yeah, my question is, do we have special cases where we use these differential pairs, or we can use it at any place?
Yes, yes. There are special cases. You cannot be routing everything as differential pair. A typical example is if you check, if we go to our circuit, you realize that between our USB port, the USB port of our Arduino, there are two signals, D plus, D minus, and the USB bridge, which is our FT232RLIC. We use differential, we will be using differential pair routing. Okay, we'll be
Okay.
using differential pair routing. So when we go there, you see. Now, one key thing, this differential pairs have to be very close to each other. Okay, if you put too much spacing between them, then there could be an instance where the noise will not affect them equally. Okay, and if the noise doesn't affect them equally, then you have a problem because they won't cancel out. Is that okay? For them to be, for them to work as intended, they have to move at the same. So the signal has to travel at the same speed on both lines. Is that okay? So that also means that if you don't route them well, and maybe we are out of space. So if you don't route them well, right? So let's say the top signal one way or the other arrives. So let's say there is some time latency or time difference between the signals, then you have a problem, okay? Because the signals will not arrive at the same time. So there could be an instance where, let's say, if an error happens on this at this point, okay, it may not affect the other one at the same point. That means this noise would arrive at the receiver at different times, and it will not be able to reject them because at that point, okay, so let's say I'm measuring the voltage at this point with some device, let's say voltmeter. You see, at this point, my recording, my value will be affected by this noise, but because of the time delay, this noise, the noise on the other line hasn't gotten to this point yet, right? So the reading I'm going to get is going to be this without this, and that means the noise is not going to cancel out. Is that okay? So when you are routing differential pairs, you have to be very careful about this. So during in differential pair routing, we always make sure that the length of our traces and their impedance match. Okay, their impedance should match their trace length. So you will hear of something called length tuning. Okay, length tuning. So this is a technique that we use to ensure that the traces are all having the same length, just to ensure that the signal traveling on them arrive at the receiving end at the same time. Please, is this okay? Yeah, Kwame.
Yeah. Please. So a common example of the application of this is the USB cables we use in the
Exactly.
everyday life.
Exactly.
Okay.
Exactly. So if you open a USB cable, you will see that the D plus D minus lines have been twisted. Okay. It is also a means of this, we call them twisted pairs. It is all because of this common mode rejection thing. Okay. So that when they are bundled together like that, anytime there is any aggression on them, it affects both of them. Is that okay? So the noise would arrive at the same time, and the receiver could reject them. Is that okay? So every good USB cable should have that D plus D minus twisted. If yours is not, please, you're going to have issues with that. And every good USB cable has to be a transmission line. So they should have this shield around them, some metal wire mesh around them. That is supposed to serve as a Faraday cage, preventing signals from entering or leaving the cable. Is that okay? Yeah. Any other question? Yeah, David.
Yeah, my question is somehow a bit funny in the sense that like you've explained that differential stuff like that. What if is there any is there any simulation stuff? You can't be perfect on the process of routing. So is there any
So I'll be demonstrating it in the process of routing. But then if you want to simulate, there are tools for that. But unfortunately, I don't have any of them. I don't have any of those tools. But you can actually simulate how energy moves on the board.
all right?
Please, any questions? Any questions? Any questions? So with all these things in mind, I am hoping that now when we go to the PCB routing and I'm mentioning some of these things, you wouldn't be too lost. Okay. So we still have 30 minutes. Let's take questions for the next maybe for the next 5 minutes. If you have any questions, any suggestions, or if there is any senior member, senior engineer who also has something to add up to, or maybe I mentioned something that maybe needs correction, please just draw my attention to it. Okay. Yeah. Okay. If no question, then thank you for the journey. Let's now get back to our PCB where we get to apply the things that we have been talking about. Okay, thank you. All right, so I'm exiting from here, and then let's switch to keycard. Okay, so somebody asked that can you actually just place components anywhere you want on your PCB, and I said that no, because if you don't place them well, you end up introducing a lot of inductances on the board, and that is not ideal. Okay, so you can see that if you look at these capacitors, I've put them very close to where they are needed. Is that okay? Very, very close to where they are needed. Now, those who were also asking about a practical scenario of the differential pair, so these two signals here, we'll be routing them as differential pair. Now, to route something as differential pair, keycard requires that they have the same base name, and one should have a plus, the other should have a minus. The moment you do that, keycard understands that it's a differential pair. Another way you could do it is use P and N, right? So I could have made this D underscore P, D underscore N, and also keycard would have recognized it as what a differential pair. Now, let me mention that you generally two layer boards are not good for high speed devices like we're about to do, right? We are still using USB 2.0, so that is not much so far as we pay attention to our impedance matching and all those kind of stuff. Okay, yeah. So that's just by the way. So when I am routing, what I usually do is to route sensitive signals first. Okay, very sensitive signals first. Very sensitive signals first. So we still have some time. Yeah, let's route. Okay, so this differential pair USB I think has to meet an input impedance of 92, or is it 120 or 92? Or we can just Google it to find out. We have to meet a certain input impedance. So you can Google inputs, and I explain input impedance, the concept of maximum power transfer. Okay, input impedance for USB 2.0. Okay, it defines a 90 ohm input impedance. Is that okay? So this means that the trace that we are going to design for transmitting this signal has to have an input impedance of 90 ohms. Is that okay? Now, there are also situations where you hear of 50 ohms. So always check with your device data sheet. Is that okay? For USB, it has to be 90. Is that okay? Now, usually it is very difficult controlling impedance on a two-layer board. So we're going to try as much as possible. There is actually a way, and I think Zach did a video on it explaining some things that you could probably do on a two-layer board where you could probably not worry so much about the impedance matching. Okay, one of it would be, first of all, bringing the making the trace very short. Is that okay? I think he did some calculations. I don't. It's quite. It's been a while I watched that video, so I don't remember it that much. Okay, so you can actually put yourself in a position where you don't have to worry about impedance control on two-layer board. Okay, it is somewhat easy on four-layer board, but on two-layer board it's quite difficult doing it. But we can put in some rule of thumbs to ensure that we get closer and we don't end up having so much loss of energy on our signal. So one of the things that I'm going to do is to route these things as short as possible. Okay, so that's why I put this IC very close to this connector. Okay, and I'm also going to fill around the traces with ground. I'll make sure they are surrounded by ground. When you do that, we call that coplanar ground. Okay, so when you have a trace moving through and you have a trace moving on the board and you have ground signal or ground plane around it, surrounding it, we call it a coplanar ground. Okay, so with that said, we can actually, in fact, I think KiCad has this. Let me see, I haven't used it before. Let's try and see if we can play with it. There is this calculator here. Let's see if we can use it to calculate, give a clue about oh wait, in our board stack up there is a place for impedance checking here. Okay, physical board. Okay, so we set an impedance control. Do we get to measure it here? Nope, nope, not here. Okay, so let's go to the calculator and see if we can. I haven't used it before actually. I usually, because I've been printing my boards, usually when I do this impedance stuff, I do on four layer, and GLC PCB actually has a calculator, so I use that one. It's quite straightforward. Okay, so right now we want track width. Okay, track width. I'm seriously seeing stars over here. Okay, transmission line. Yeah. Okay, so you can see microstrip, right? Remember what I said about microstrip? If the base is having a plane and your signal is the other side of your signal is in the air, it's called microstrip. This time I want to create it as a coplanar, but coplanar with a ground plane. Yes, that's how we want to do this. And if you want straight line, that means the signal will have to be in between two planes. Okay. And what we are trying to do, yeah, we want to do something like this coupled, because you are doing differential pair. Uh, Differential pairs. Yes. So we want something like this. Okay. So what should be the spacing between them, and what should be the width that we could use? Is that okay? That's what we are trying to look at right now. Now this ER, I think this ER has to do with the dielectric constant of the FR4 material. And I think it's 4.2 or 4.6, something like that. Zach has been mentioning it, but I haven't taken notice of it. I have no idea what this parameter is. That's just so funny. So maybe for now, let's just leave this place empty. Now, the frequency that will be the frequency of our signal, which will be frequency of USB 2.0. That is 240 megahertz, right? 200 repetitive pulse at 240 megahertz. Okay, so let's put in that megahertz. We want 240. I just hope I'm doing the right thing. Okay, so if we do this, analyze. Okay, physical parameters, the width. Okay, so let's say if we, is this thing something that has been generated because of this input? Okay, let me try changing this and see if those parameters will change. I haven't actually used this before. Okay, I think there are parameters you have to set. Okay, so technically this guy, what is he trying to tell me now? Okay, so if I use a width of, let's say, 0.26, spaced at about 2, yeah, let's maintain 2, and then the length is 50 mm, right? Oh, I should synthesize, analyze. I'm so confused over here. Okay, so does this mean these are what the thing, the input differential impedance? Okay, you get a differential impedance of 115. Okay, let me change this to that and see. Okay, so it is rather increasing, but we need something around 90, right? So if I set a weight of 2.6 and reduce this to 2, I just hope I'm using this 2 rightly. Yeah, so we've managed to get this. Now, do you remember I said that we could adjust this width and then the spacing and stuff, right? So that's what I'm trying to do. But unfortunately, we don't have control over the board thickness. JLCPCD will probably be doing that. So let me just do this. Let me just do this. Let me just do this. Okay, electrical parameters. We need. I have no. Okay, this. Let me set the 92 over here and see. So as a newbie to this, as you. Okay, this not changeable. Okay, so for a trace weight of 50, if my spacing is okay for GLC I can't go below this. What about I use point 0.3? How do I get this? If I use point 0.3, analyze. Okay, so 95. That is not so bad. But actually, the spacing that will be routing, I doubt we can have point 0.3 over there. I doubt we can have. But at least if 90, the differential impedance will be 95. I mean, we are still around that value. Okay, so that is cool. Maybe point 0.5. Oh, good, we get it to 88. So maybe 0.2, 92. Yeah, I think so. Let's see if we can actually configure. Let's try and do the configuration. So I'm going to define a differential pair net. Or come here. differential pair nets. Okay, so net classes, I'm going to define one, call it diff pair, 90 ohm, because I can have, so 90 R diff. Okay, so the clearance, so this guys here, this way we what we have to. So you remember the differential, the spacing, it was 0.2, right? And then we to attain the 90 something, we set this to I think 3.2, 3.1 thereabout. But this will also depend on the fact that we will have that amount of clearance over here. So I'm going to change their individual weight to the same differential pair weight. Remember, you should always keep your traces same weight to avoid reflection. Okay. Let's set this to 0.6 just in case, and the whole, yes, the whole, we will leave the whole at 0.3 so that we have good annular rings. Okay, so let's see. Now to route a differential pair, you can come to routes. Okay, route. So you see that we have route differential pair, route signal pair, single track. Okay, so I'll choose differential pair. The moment, because it has been labeled as a differential pair, the moment I click on one, you see keycard automatically picks the two. Okay, that is the reason you have to label them as what? D plus D minus. That's the convention that keycard uses. Now, looking at the path, this C13 capacitor is going to influence my work. So I'll cancel it and then shift this C13 capacitor a little bit away to allow room. Okay, I can compromise on the cap. Now, if I do this, then let me rather rotate this cap so that its signal gets closer. Yeah, so I think that is good. Okay, so let's go and route the diff pair. So once again, you can actually also select it from here. You long click it, so you click on this small icon here. It's actually difficult. This thing, I don't know, it's very annoying to pick it. So just come to route and route diff pair. And fortunately for us, this IC and the port they really map is direct. Okay, there are a lot of ICs that, in fact, the QFN version of this same IC, you have a crossing over. Okay, but fortunately, so what we do is we maintain this, and okay, so you can see that there is a problem. There is a problem with clearance for us, right? There's a problem with clearance because we couldn't continue. This is because the spacing in there. So if we try to start from here, oh, fantastic. So that's even better. So we move from here and then, so period. That's how we route our differential pair. But there is one more thing. You see, this line here would definitely be longer than this, and you can actually check. You can actually check it. You can come to route and come to length tuning. Okay, so length tuning, and here you realize that we don't have the things are not the same. Okay, let me pick the single net tune and let show you the length. So single net length tune. Look at this. You see, it says that too short. Is that okay? Okay. The too short is because of. But look at this. You see, this particular trace is 10.12 mm in length. Okay, it's very short. It's just 1 centimeter. Okay, so it being short even means that yeah, we are in a good zone because now we can to some extent even in remember the tortoise and cheetah analogy, right? If the cheetah is running 1 meter and it can run it in a second, it's almost like the cheetah doesn't even have to move, right? So in this case, if the signal can travel faster, if the signal travel faster and it's traveling on a very short path, it means that it will be like the signal is not even changing at all. Okay, because anytime we want to measure, we will get it. Okay, but this one is 10.12 nanometer. sorry, millimeter, but the one here, let me pick the same tool, single track tune. The one here is 9.34. And you remember what we said about differential pair. You have to make sure that they have what? The same length. Is that okay? Very, very important that they have the same length. So how do we ensure that they have the same length? We can actually tune it. So to tune it, we can select tune differential pair. Okay. And what I'm going to do is right click and set some parameters. Okay. So looking at the signal, the longest was 10 point something. So I'm going to set the track length to 12 mm. Okay. And for now, I'm going to leave this, the minimum spacing, yeah, I will leave it like this. And then I'll come back and try to tune. So I think in this case, it's going to be very difficult to tune them together as I'm sorry, because the difference right now is very small. It will be very difficult to tune both of them as differential pair, but let's still see. So you can see that it's just like a little gap, a gap of 2.4. So moving the two together is almost not possible. So, but then we can actually tune them separately. Okay, can tune them separately. So I'll pick on the single, right click and adjust and set it to 12 already. Then tune. This is the shortest guy among them. Okay, so I will tune it. Now, it's usually a good idea to tune from the input source, okay, not at the collection source, okay. So now you can see that I have been able to, by doing this adjustment, we have been able to turn it exactly into what 12 mm, right? And the signal, the text is now green, meaning that we are good to go. Okay, so I've tuned that, but this is still not 12. So let's try and see if we can tune it. And over here, okay, doing this to it, we can tune it to exactly 12. Okay, so now we have routed it as a differential pair. Wait, the way we have this, well, we've routed it as a differential pair and we've also ensured that the lengths match. Okay, so that's what we mean by length tuning. This is to ensure that the signals would arrive at the same time, because remember, if the signals, the positive and the negative, if there is a lag between them, then you would defeat the purpose of the differential pair, because it wouldn't be able to reject the common mode noise. Okay. Yeah, Chris, your hand is up.
Yeah, yes, I'm kind of confused. You did some settings regarding the differential pairs. You changed some settings like 0.01
Yes.
for this
So
one.
that was when I had you were talking about after I had drawn the differential pair, right?
Yeah, no, before you started drawing, you made some settings. So I want to know the relationship between what you just the settings you made and
Okay.
what you
So before I started drawing, I picked these two route differential pair, because the signal that we are going to route is a differential pair. So we can't route them. Now we can actually route them as single lines, but it's generally not a good idea. Okay, it's not a good
okay.
idea. So I selected this. Now because it is a differential pair, the moment you pick the first signal, it automatically tag the second signal along. Okay, because
Yeah.
as part of our differential pair, it's supposed to have the same separation. Okay, except the fact that over here, so you can see that over here, even though I've done these changes, they are kind of symmetric, okay, which
Yeah.
is also a good thing. Then after we do it, the line, the trace that was beneath wasn't having the same length as the one upwards. And of course, that would happen because this one travels a longer distance than this. And we said that for differential pair, you have to make sure the trace lengths are actually what the same. Technically, what we are concerned about is the signal velocity or the time of travel. The signal have to travel at the same time, reach destination at the same time. Is that okay? So even if you are routing your trace through any path and they manage to arrive at the same path, that is still okay. But the rule of thumb is to set the length of the traces equal. Is that okay?
Yeah,
Now, initially,
yeah,
yeah.
I understand this part very, very well. It's like very clear. But where I'm confused is that the settings you did for the differential pairs, how does it affect the lines that you're, because you declared, it's like you declared those that value, you wrote differential pairs and now entered the values. So now you now came here to pick up the this thing and
Are
then
you talking about what we did? Are you talking about what we did here? I'm coming. Are you talking about what we did here?
exactly, exactly.
Okay. Actually, yeah, thank you. I didn't actually assign the net. Sorry. I didn't actually even assign the net. That means it was routing with this. It was routing with this stuff here. Actually, yes. So yeah, let me assign the diff first. So you see, it was routing with the default. Thank you for drawing my attention to that.
Thank
Okay.
you.
Yeah. Yes. So we actually have to cancel what we've done because definitely something is going to change. Right now, the signal has become thicker. The width that we are using have become thicker. Sorry. So if we come back to route as diff pair, wow. Yeah, it is still seeing it as diff pair, but fantastically, look at this. If I select this trace, you see, it's the net class is on it, the minimum clearance is 2, and then yeah, it's actually the diff pair. Okay, so then that's cool. That's cool. So definitely, then what I did afterwards was like these traces do not match. Okay, so the first thing, right? Let me try that thing again. I'm going to try to tune them together. Okay, and see if I could get them to match, but it is almost not possible because of how the things have been arranged. Okay, it's almost impossible. So the only way I could probably solve this is to tune them independently or individually. Okay, so I come to route and select tune length. Okay, but then you first have to check what is the length you are trying to tune, the final length you want to achieve. If we check this, you realize that you can see that it says too short. The actual length of the trace right now is 9.78 mm, right? And if you look at this one too, this one is 8 point what? 8.3, right? But I've said that when I right click and go to, if you right click and go to the length tuning, I have set this track width to be 12. Is that okay? Now I can actually even set it to 10 or set it to the longest value. Is that okay? But I'm just going to leave it at 12, and then that means if I'm tuning, it has to meet 12. Is that okay? So the first thing I'm going to do, in fact, let me adjust this thing and route it again to make it nicer a bit. And also, so I'll rather pick it from here, travel, so that I have enough space, come here and then branch it like that. Okay, so now pick the single length tuning. We've already done the settings. I want it to be done nicely. Hmm, it's going beyond what we want, so just drag. What I'm doing right now is trying to drag along to see if I could get it. Okay, so probably let's adjust, and instead of a 12, let's make it a 10 and see if that really helps. Okay, take route, single length, single track again. Yeah, so just doing this, we reach a 10. Just doing this, we reach a 10. Oh, okay. I think if I set it to a 10, then let's try differential and try to route. Sorry, try and do the tuning differential by using differential. We want a 10. Yeah, it looks like it's not going to batch. So let's go back to our single route. So move this, and yes, I can accept this. Move this. This is this is too long. Okay, so this is too long. That means the length we chose is not right. So let's try 11. Okay, We just want to be able to tune both of them to the same length. Okay, so 10.9, that's acceptable. And just this, maybe make it symmetric. Just move it along. This gives us exactly 11. Yeah, I'll take this. I'll take this. But I think this would affect our impedance. So let me see if there is a way I could make this rather move. Aha. So this, something like this should be better. Yeah. So we have learned tuned it. We have also routed it as a differential pair. Okay. We also did the settings such that we would meet the input impedance. But remember, I said that because this is a just a two-layer board, matching the input is going to be difficult. So one of the things we can do to mitigate that is making sure that these distances are very short. And actually, this is just 11 okay, just a little bit above 1 centimeter. If you take your ruler, just a little bit above, if you measure 11 millimeters on your board, that's actually the length of this. Okay, so it's actually very, 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 very short. Okay, very, very short. All right. Our time is up for the first session. So the next session, we are going to continue with the route and complete it. We are definitely going to complete the route in the next session. So see you. If there is no other question, then see you soon. Thank you.